We've got actually two keynoters for this go-around here, Chris Lamb and of NVIDIA and Mike Kagan from Mellanox. So I'll introduce Chris first. He's going to be the first speaker. And he leads software engineering for the CUDA platform, DGX systems, and data center distributed systems such as Kubernetes and NGC. He works on software that spans supercomputers, clouds, workstations, robots, and self-driving cars, which is a really hot spot for NVIDIA right now. He's been working on embedded systems, microwave communication, that sort of stuff, and has a BS in computer engineering from the University of Illinois. And he was just telling me that he's a father of a couple of young kids, a 3-year-old and a 5-year-old, and they keep him so busy he doesn't have time for other outside occupations that he really likes, like flying his airplanes. So also he's going to speak first. After that will be Mike Kagan, who's a co-founder and CTO of Mellanox. He's also been a speaker at the Flash Memory Summit in the past. He focuses on high-speed networking, which is used in clouds, websites, and supercomputing applications, and has worked at Intel after getting his BSEE at the Technion in Israel. Something that he's notorious for is whenever Mellanox visitor comes by their Israeli plant, he takes them out on hair-raising four-wheel drive rides out in the desert. So without further ado, let's welcome Chris Lamb out to the stage.
Hi there, thank you and welcome. So I worked on CUDA for about 12 years now. I started when the team was about 7 people. It was a very small team looking to change the world. And right from the beginning, I/O and keeping the GPU fed was one of the biggest challenges we had. So I/O, asynchronous I/O, high-performance I/O has been a real crucial part of the story of accelerators right from the beginning. We started off with fundamentally asynchronous I/O in the CUDA APIs. We invented the GPU Direct technology for interoperating with networking cards for scaling out GPU systems with Mellanox very early on. And recently, we developed NVLink, which is an interconnect to tightly integrate GPUs together, all to basically fight off Amdahl's law to keep things scaling. And so I'm here to share an exciting new chapter we have in accelerators and I/O, kind of inspire you with some of the things that it's going to enable us to do, and also motivate why it's coming at a really crucial time. A crucial time because Moore's law has ended. We're not seeing the scaling by far that we used to anymore from serial performance and performance per watt in a serial core. But the demand for computation continues to explode, and the data that's driving that computation is exploding as well. In addition, we're entering this new phase of computation with a new paradigm with modern AI and machine learning techniques, where we're really getting to the point where people can start saying that software is writing software, and that software is written ultimately by data. And so it's changing a lot of the assumptions that we make as we want to continue scaling the performance of data centers in the future. It's really been, I think, widely accepted at this point that acceleration is the way that we're going to drive performance in the data center going forward. And that's because this demand is really extreme. It's exponential in multiple dimensions. We have exponential growth in data that's being generated, and increasing that data is really unstructured. You don't have the time to curate it or to think ahead about how it should be formatted for the ultimate processing that you want to do with it. You just need to keep gathering that data as fast as you can. One of the things I like to talk about with my team is to just think about the fact that most of the data that will be processed through these systems in the future hasn't even been generated yet. We don't know what format it's going to be in. On the other hand, the algorithms that we're developing to process that data are also growing in diversity at an exponential rate. And what this means for the people who are developing those algorithms is that they need to balance and test and validate those algorithms against existing data sets, new data sets. And so the demand of new algorithm development is also driving an incredible growth in the amount of processing power needed. And this is really clearly shown by the computational demands of complex AI models and how that is growing over time. And it really highlights this fact that you've got this kind of double exponential driving growth. And so ultimately, the architecture that we have to address this with acceleration is fundamentally grounded on something where you've got a programmable accelerator that can work across multiple domains, because you really have a diverse set of workloads that you're going to operate on in a data center. And you want to make sure that with a single architecture deployed widely across that data center, it can flexibly adapt to process across all those different domains of software and algorithm that you might want to throw at it. And this is one of the reasons why NVIDIA GPUs are the most widely adopted accelerator in the industry, is because they have this property, but also for another key fact, in that this is not just a purely hardware problem or a systems problem, but it's a full stack software optimization problem, where you need to first design the systems in hardware, but also design the drivers, the operating systems, the libraries, frameworks, ultimately the applications that sit on top of this, all together so that they can take advantage of these continually advancing parallel architectures. One of the ways that the industry and we have tried to help make this more adoptable is the use of containers, where we have on NGC, which is a registry of these fully optimized GPU-accelerated application containers that have these tuned software stacks end-to-end. We have that up on a registry called NGC. An example there might be all of the major AI training frameworks, PyTorch, TensorFlow, MXNet, et cetera, science and simulation workloads that are very compute and data intensive, or Rapids, for example, which is an open source GPU-accelerated machine learning and data science set of primitives that might help with, say, traditional extract, transform, and load, or SQL queries that are used to drive the very beginning of a data processing pipeline. So it's really this full stack optimization problem that we're trying to solve. So now let's dive into one particular I/O specific area of this kind of full stack optimization challenge. And that is data movement. And so a trend we see is that because power is dominated by data movement, you really want to minimize the amount of data that's moved, because ultimately most of your systems are power performance constrained. And so you see this trend to densification of the physical structure of data centers. Because Moore's law may have ended at the silicon boundary, we still have the ability to take multiple components and bring them together in packages and systems. And so you see this sort of multi-component densification. This is kind of like a time machine, in that with one of these dense systems, you can look at a capability from an application standpoint that's on the very cutting edge of what's possible today. But on the other hand, it's a bit like a time machine in that it's showing you what more commodity scale-out systems are going to look like another click of technology into the future. And so it really helps us look at the kind of software that we need to build to allow these paradigms to continue to scale. So with DGX-2, which is a very dense system with 16 GPUs, we connected the GPUs together with the NVLink fabric, which allows the GPUs to operate together coherently on a 0.5 terabyte of shared high-performance, high-bandwidth memory. Huge bisection bandwidth, 2.4 terabytes per second between this. And ultimately, that made it much more simple for CUDA applications to scale across this architecture. If you want to manipulate a data cube, if you want to search through it, sort through it, scan, index it. But getting the data into this machine was still quite a complex problem. As you can see from the system architecture here, you had to, at the application level, orchestrate across multiple I/O devices, inputs, outputs, balance them. Think about that for just this machine, and then think about that for future machines or other machines that might have slightly different configurations. As a software developer, really, you want a paradigm that is simple to program and reason about, high performance, it always gives you the best performance that you can get out of the system you're on, and ultimately flexible, so it can adapt across multiple different deployment paradigms. And so that's the problem that we've solved with this technology, GPU Direct Storage. Ultimately, to give the software developer a view of the system that's simplified like this, where they think about the GPUs, the processing they're doing, and the high-speed I/O that can deliver the data that they need to process from something that is effectively infinite storage, where you're storing all the data. Simply put, it puts all the GPU I/O available in the hands of the developer. Another key thing here is that it eliminates an extra copy of the data that might occur if you're staging it manually through system memory or through another framework there. This removes a tier of complexity, but in a lot of systems, it actually removes a bottleneck. And that's one thing to highlight here. In this system, you can actually see that the I/O available over the fabric outside the system is actually bigger than the amount of bandwidth available to the system memory through the CPUs. It introduces the opportunity some very interesting new ways to approach certain algorithms that we'll see later. So another challenge here is we're trying to scale this architecture. That's one system driving 100 gigabytes per second of I/O out over the fabric. Now we're building data centers of these systems. And we want them to be flexible and efficient. And so disaggregation is a really key trend we're seeing that allows the data center to both scale the storage independently from the compute, but also make sure that it's attached to the compute flexibly and is used efficiently. A really key thing here is end-to-end offload of all of the various bits of processing across the entire stack from the application down through the storage workload, down to things like replication, deduplication, encryption. These processes need to be offloaded in hardware and on the high bandwidth path between the GPU and the storage, or else they're basically just pulling you out of the fast path if they're getting in the way. So here's an architectural overview of the GPU Direct Storage stack. It's pretty simple. There's a cuFile API, which is a simple extension to the CUDA APIs, if you're familiar with GPU programming on NVIDIA, that allow you to take traditional primitives like reads and writes that an application developer might use on a standard file system, have them operate both on GPU accessible memory, but also compose with asynchronous primitives that are really key for accelerator programming, such as streams and graphs for orchestrating the overall flow of the program. Then there's the NVFS driver API, which is a very simple kernel-level API for kernel drivers, kernel modules that are in the storage stack to interoperate with this offloaded I/O path. And so when we look at the performance expectations that we want from this kind of system, it follows a very simple roofline model, where we want very early in the small sizes of I/O to reach up to a peak bandwidth that's basically determined by the speeds and feeds of the I/O provisioned in the system. And so based on the I/O provisioned, we get a very simple expectation of performance for the application. So let's take a quick look here at what we actually get in practice. So on the left, you can see measured bandwidth from a benchmark that's very FIO-like, doing synchronous I/O, multiple synchronous I/O, using this GPU Direct Storage path on the top here, following that roofline model. We get that. Compared to other approaches, such as using a standard page cache-based approach and then copying into GPU memory, or one where you've done a little bit of tuning even, and you're using ODirect flags and bypassing the page cache to try and make it more efficient. Neither one really comes close to what's possible in terms of making that simple roofline available to the application. On the right side, you can see another really key benefit of offloading the I/O, which is that the amount of bandwidth you can drive per CPU core is incredibly high. It's actually kind of hard to see it compared to the other lines there, but it's about 10x and remains all above the other lines for every single transfer size. So let's take a look at what this means for an example application. So here we have a test application that's modeled on the TPCH Query 4 benchmark, which is a benchmark suite that does OLAP business decision queries, operating on two sizes of data sets, one that's about a 1 terabyte data set, one that's about a 10 terabyte data set here, using two different approaches on this same system. One approach is paging this through system memory and copying it back and forth as optimally as possible, and the other one is using GPU Direct Storage to operate via the GPU directly off of disk on this data. And you can see that there are pretty dramatic speedups in end-to-end application performance. Here we've kind of unpacked the whole benchmark, including all of the setup and the load for all the acceleration structures that you need for paging through that memory and accelerating it, as well as warm-up queries. You can eliminate all of that when you're operating directly off of disk. The other thing you can notice on the right-hand side, where we've zoomed into just the GPU Direct Storage versions of this test case, operating directly off disk, you can see as you move from the 1 terabyte to 10 terabyte size, and you're really out of the system's capacity to cache any of this data, that the two queries, the green and the blue bars, are actually about the same duration. One is the first query, one is the second. And this tells a really interesting story, which is when you don't have to do a lot of system setup and acceleration data structure setup and operate directly off the raw data on disk, it's very easy to change the data set that you're operating on without paying a big penalty and resetting up these structures. So we have more information if you're interested in the technical details. We have a dev blog on NVIDIA.com. There's also a link there to register and indicate your interest if you want to provide feedback, or if you're interested in extending this to serve a different kind of file system or an interesting storage device. We're absolutely happy to hear from you. Thank you very much. And now I want to hand over to Michael, who's going to talk to you about the kind of high-performance storage networks that make all of this possible. Thank you.
Yeah, thank you, Chris. Good afternoon, everyone. After Chris talks, I'm sure that everyone is alert and no one sleeps after the lunch. And I'll be talking about how to deliver the data from the storage to the computing. So in a sense, we are at Mellanox is almost resourcing company, because as Chris mentioned, data writes the programs or makes the applications, and we are delivering the data from the storage and all these wonderful storage solutions that talked so much about this conference. So we are a networking company that have a full connectivity from very low level, starting with cables, adapters, switches, and we can connect any storage to any compute device. And we have been working with NVIDIA for many years as of now to optimize this path from the storage, from the data archive, from the place where data is stored, to the computing. Our network solutions today run from 10 gig to 200 gig, both InfiniBand and Ethernet, and we have the most advanced solution in terms of efficiency, bandwidth, and latency. So this is the schematics of the DGX box Chris talked about. So once you have a single box, you have fairly significant amount of GPUs there, and there are 16 of them, and you have also local storage. But the bandwidth between the storage to the GPUs is limited by the PCI Express topology here. And also the ratio of, there's a fixed amount of storage per compute power. So there's a fixed ratio of computing versus storage. And therefore, there is two topics to solve. One is the bandwidth from the storage to the GPU. In this configuration, it's every GPU can get 12.5 gigabyte per second. And the other one is the scalability and composability. So the way to solve the bandwidth issue is just to connect the storage over the network using InfiniBand or Ethernet. So it simply doubles the bandwidth to every GPU. We saw the keynotes earlier today about talking about 25 gigabyte per second data rate to the GPUs. So this stuff works today in production. So it can be either InfiniBand or Ethernet. It can be NVMe over Fabrics using advanced RDMA technologies. We will talk about this a little bit. And therefore, the bandwidths and we have all the offloads required to move the data from the storage to the GPUs, and we obviously deploy GPU direct technology. So once we connect to the network, we are pretty much on the path to solve the issue of composable infrastructure. We can scale the storage independently of the computing, and therefore the local storage can be either removed or can be used for local caching. And that's why it exists. It significantly improves the total cost of ownership, high availability, and basically storage resources become unlimited. You can have as many devices, storage boxes as you want to connect it through the network, and it is all over more efficient. And obviously the next step is to scale the compute power if you wish. So you have the fully composable infrastructure of computing and the storage. And using the high-performance interconnect, you have the remote storage access at the same cost and the same performance as if it would have been local storage. If you need more CPU, more compute power, you connect more DGX boxes to this machine. If you need more storage, you connect more storage. So there is many advances in the storage media technology, and this Flash Memory Summit basically talks about the most interesting advances of this. So moving from spinning disks to flash devices, SSDs, actually improved the media access time by 2 or 3 orders of magnitudes. Once you improve this media access time so dramatically, you need to make sure that the overhead of accessing this media, which is bandwidth, latency, and the protocol overhead itself, scales down accordingly. So NVMe software stack removed significant amount of software that is required to access the local devices based on SCSI, and NVMe Fabrics actually enable to extend the reach of the NVMe device to the network. So now it's, again, composable infrastructure, and NVMe Fabrics, which is based on the RoCE RDMA, working both on Ethernet and InfiniBand, enables to access NVMe storage over the network at the same performance and the very similar latency as access to the local devices. And again, scalability is unlimited. So RDMA is the technology that enables to access remote direct memory access. You access the remote resources directly, remote memory directly, so you can move the data very efficiently. And RDMA is actually the key technology for composable infrastructure. All the advanced protocols are based on RDMA, and there is RDMA is then the production in the multiple sites. Alibaba running RDMA at large scale. And here you can see the Microsoft, they use RDMA in production for their storage solutions. It is 2 times faster than the TCP. They're using RDMA over Ethernet. And it's 1/3 of the CPU. You can get twice the performance of the storage using RDMA. That's Microsoft Storage Spaces. There is a reference to the video demonstrations from Microsoft that you can look at if you wish to. So the ecosystem of RDMA evolving dramatically. It made quite a few stages, especially in the storage space. It is started with the block storage. iSCSI was enhanced with the ICER, which is iSCSI extension of using RDMA, and the performance was improved fairly dramatically. I talked about the file system over RDMA. That is the Microsoft or one of the leaders of driving this technology. And RDMA also is using in the key value store. And last but not least is persistent memory. The persistent memory access is, persistent memory technology on its own requires remote access. It requires RDMA because once you claim something persistent, it means for high availability, you need to replicate data, you need to mirror data, you need to have it on more than one machine. And therefore, RDMA technology is base technology that will actually make persistent memory deployable. And the InfiniBand Trade Association works on the protocol extensions of RDMA, enhancing RDMA technology to carry the persistent memory semantics over the network. And this is also in the development in our products that as of now. And last but not least, all the platforms and all the major players in the industry, Linux, Windows, VMware, and the like, uses RDMA today. Oracle uses RDMA. It's old story. They use RDMA in all their Exadata, Exalogic, and Cloud appliances and products. So with RDMA, with NVMe Fabrics, you can actually get performance of, from remote storage very similar to performance of local storage, both in terms of latency and the bandwidth. It is a much lower CPU utilization. We have a solution that basically single SoC can be used to build the NVMe Fabrics JBOF with the pretty much zero CPU on the initiator and on the target, and you can scale the storage as you wish. In addition to just protocol of flow, there's more things that you need to do in order to access the storage. It's encryption, it is compression, and all these operations, as Chris mentioned, needs to be done in hardware to allow line rate of the high bandwidth line rate of the data access, and also low latency, let alone the CPU cost that is required to process the data doing the encryption and compression at 100 gigabit and above. And today we have solutions that enable to compress the data and encrypt the data at these rates. So these are the actual systems that qualified and certified, and you can buy them, different configurations of storage vendors and storage servers and DGX boxes. If you need, and this is the configuration that you can actually buy out there. It uses Mellanox technology embedded in the DGXs, so there is a full connectivity of high bandwidth connectivity from the storage server all the way down to the compute machine. So the network moving forward, today we deliver 200 gigabit per second data rate on both InfiniBand and Ethernet links. It's in production. Soon we'll have 400, so both InfiniBand and Ethernet are moving forward with the bandwidth and reducing the latency. And this will be, this roadmap of technology is pretty much going to be matched by our technology and our products. And the next thing also talked about quite a lot on this conference is different storage advances. One is having the SSD directly attached to the Ethernet. We talked about the persistent memory. It is critical to have to enable to access persistent memory over the network in an efficient way, and RDMA is the key technology. And then storage the things. There is multiple ways and multiple reasons to have smarter storage and more processing on storage. One of the examples is was presented, well, other ideas was presented by Facebook at OCP earlier this year. Basically, when you go down the stack on storage access, due to memory storage access amplification, the bandwidth is much higher. If you go higher up to the stack, you can reduce significantly the bandwidth required to access the storage device. And we here have a great partner that we worked with for a while on the computing space, which is NVIDIA. And our merger with NVIDIA that is awaiting the approval from the authorities seems to be so natural that the editor of the program actually swapped our names. He said Chris from Mellanox and Michael from NVIDIA. Actually, it's the other way around. Chris talked before me. He's NVIDIA software VP computing, and I'm a CTO and co-founder at Mellanox. And with that, I'll thank you for your attention.